Alright, today we're going to look at a lot of different stuff. We're going to kind of cover a lot of definitions. So we're going to talk about the complement of an event, exclusive versus inclusive, given that, dependent, and independent events. So we'll talk about all of these. This is kind of the outline for today. It is kind of note intensive, so we'll try to plow through it as quickly as possible, but it's going to take some time. So buckle up. We're going to start out with this scenario. It says if the probability of you getting a test question right is 70%, what is the complement of this scenario? And so the notation here is if event A is getting a test question right, then the probability of A is written as P of A. That's just the probability of A. And that probability is 0.7 or 70%. And so the complement is written as probability of A. It looks like to the C power, but that just means it's the complement. So let's look down below. What is the complement of you getting a test question right? Well, the answer is you getting a test question not right. So the complement is 30%. So the complement is basically just everything else. So let's look at a couple other examples to hopefully clear this up just a little bit here. Given a standard deck of cards, consider what the following events. Event A is you draw a spade. B, you draw a 7. Event C, drawing a red card. And event D, drawing a face card. So let's figure out the probability of each of the following. Probability of A, what's the probability that you draw a spade? So that would be, well, there are 13 spades in the deck. So it would be 13 out of 52. Which reduces down to 1/4. Okay, so the complement of that is not drawing a spade, which is everything else. So that would be 39 out of 52. That would include hearts, diamonds, and clubs, which is 3/4. Okay. Event B, drawing a 7. Well, there are 4 7s, 4 out of 52, which ends up being 1/13. So the complement of that would be all of the other cards, so 12 out of 13. So if you notice, these probabilities, 12 out of 13 and 1 out of 13, they'll always add up to 1 or 100%. And that makes sense. One of them is the probability of the event. The other one is everything else, which means 100% minus the event. Event C, drawing a red card. That's half of the deck. 1 out of 2. Probability of the complement of that, that's not drawing a red card, so basically drawing a black card. That would also be 1/2. And then event D, drawing a face card. There are 3 face cards for each deck. And there are, 3 face cards for each suit. And there are 4 suits, so there would be 12 face cards total out of 52, which reduces down to 3/13. So the probability of you drawing a face card is 3/13. So the complement of that would be not drawing a face card, which would be 10/13. Alright, so complement is basically 100% minus the event that you're given. Alright, let's look at the next idea. The next idea is mutually exclusive versus inclusive events, and this is tied into the previous thing that we had just talked about. So exclusive events are events that cannot happen at the same time. The example I gave is you cannot draw a card out of a deck and have it be a diamond and a black card. Diamonds are red cards, and so it can't be a diamond and a black card at the same time. So inclusive events are things that can happen at the same time. You can draw a card out of a deck and have it be a diamond and a 7. That would be the 7 of diamonds. So those do overlap. Diamonds and 7s do overlap. So the way I like to think about it is looking at it from like a Venn diagram perspective. Exclusive events, there is no overlap here. So maybe we could write down a note here. There is no overlap. examples of this, with a deck of cards, it'd be like red cards in one circle, black cards in another circle. You could also think of it as boys versus girls. You can't be a boy and a girl at the same time. I guess anything where it can't be. And so basically you could think of it, well, I was going to say complement and event, but that's not always the case, so ignore that. So anytime where things can't be overlapping. Inclusive is where they do overlap. So this would be like, say this circle represents girls, and this circle represents, I don't know, volleyball players. So in the middle here are girls that happen to be volleyball players. So there are some boys that are volleyball players. They would be in this section here. We'll just kind of in that section. This is boys that are volleyball players, and this over here, I'll switch colors. This region here is just girls that are not volleyball players. So inclusive events are things that can overlap. All right. So we've got definitions down. We've got inclusive, overlap, mutually exclusive, do not overlap. And then the first thing we talked about was complement, which meant it's basically 100% minus your event. Okay, so let's look at independent events then. So independent events, they're two events that if the outcome of event A has no effect on the outcome of event B. And there's a definition of independent events that we're going to look at here shortly that it really doesn't tie into what we have right here. It's more of a mathematical definition. But if two events are independent if the outcome of event A has no effect on the outcome of the other event. And so the examples I have here are flipping a coin twice. So if you get heads on the first coin, that really does not affect what happens on the next coin. And so a lot of times, you could say to somebody, if you flip a coin 10 times and it lands heads 10 times in a row, what are the chances that it lands heads on the 11th time? And a lot of people would think, well, not very good, because the chances of that happening 11 times in a row is not good. But really, the 11th flip has nothing to do with the previous 10. So it's still 50% on that 11th flip. Okay, so flipping a coin twice, those are independent events. If you roll a die and then flip a coin, whatever that die comes up, that has nothing to do with how the coin was flipped. And so these two events are completely independent. And then lastly, if you have shuffle on your iPod, if you allow repeats, now I'm sure the iPod has some algorithm that says, repeats don't repeat the same song, right after itself. But let's just say it was truly random, just randomly selected one song and then randomly selected another song. It could, in theory, randomly select the same song back to back. So if you play, I don't know, Poker Face by Lady Gaga, if your iPod plays that, it could play it again next, or it could play something else. Okay, so we've got independent events down, and so the definition mathematically is if events A and B are independent, if and only if the probability of A and B is equal to the probability of A times the probability of B. So let's put this into place here, or let's kind of do an example of this stuff. And let's use that definition to determine if these two things are independent. So event A is rolling a die and getting an even number. So the probability of this happening is 1/2. That would be numbers 2, 4, and 6. That's 3 out of 6. And then probability of rolling a die and getting a 3 or a 4. Well, this is 2 out of 6, or 1/3. And so, based on our definition here on the previous page, it says probability of A and B, that means the overlap of A and B, has to be equal to the probability of A times the probability of B. So A and B, let's kind of draw this out and look at a diagram here. So event A, I'm going to make that a little bit bigger. So event A would be getting an even number. So that would be like getting a 2, a 4, or a 6. Okay? This is event A. Event B is getting a 3 or a 4. So the event B is that there's only one place where that overlaps. So probability of A and B is equal to, there's only one time where that happens, it's the 4, out of a possible 6 faces on the die. So the probability of A and B is 1/6, and the probability of A times the probability of B, I ran out of space here, is equal to, let's see, it's 1/2. Probability of A is 1/2. Probability of B is 1/3. So 1/2 times 1/3 is 1/6. So what this tells us is if A and B is 1/6 and A times B is 1/6, then these are independent events. So since probability of A and B is equal to the probability of A times probability of B, then these are independent. Alright, so when it says use the definition, using the definition of independent events, that is, if you see a problem in your homework, that is what it's talking about, using this. Okay, let's look at the other example, rolling 2 dice and getting a sum of 6. And so, maybe we should make a chart here. I'm going to pause it and make the chart. Alright, it's like magic. It just magically appeared. So you should have this on your note sheet. I didn't really think ahead there. So the question says rolling 2 dice and getting a sum of 6. And what I did was I colored them. The sums are all in orange. So the sum of 6 would be anything on this diagonal. So we've got 1, 2, 3, 4, 5 times where it'd be a sum of 6. And so that probability would be 5 out of 36. Oops. Five out of 36. And then rolling 2 dice and getting a sum less than 8. So that would be all of the 7s. 1, 2, 3, 4, 5, 6. And all the 6s, 5s, 4s, 3s, and 2s. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So there are 21 ways that you could roll 2 dice and get a sum less than 8. So the probability of that would end up being 21 out of 36. So if we multiply these together, we get 105 out of 36 squared. Let's calculate that. We get 1296. So we did probability of A times probability of B. That's this number. So what we want to show is if the AND part, the probability of A and B, if that equals this number, 105 over 1296, then these events are independent. If not, then they're not independent. So, probability of A and B, that's where it'd be a sum of 6 and it's less than 8. Well, that would be the sums of 6's because those are sum of 6 and they're also less than 8. So that is 5 out of 36. And these two numbers are not the same. 5 out of 36 is not the same as 105 out of 1296. So that tells me that these two events are not independent. So we can write ourselves a note. Not independent. Independent. Alright, so the definition of independent events, we just used this probability of A and B equals probability of A times probability of B. So if you're given two events, you just need to multiply them together and figure out if that's the same as the AND part, the overlap. Alright, so let's do an example where these are either dependent or independent events, depending on the situation, and figure out the probability. And so we don't have to use the definition of independent events for this. This is just a completely separate scenario. So you have a bag of Skittles with 10 red, 8 yellow, 6 green, 11 purple, and 9 orange. What's the probability that you pick a red Skittle, replace it, so you put it back, and then select a green Skittle? So the probability of selecting a red Skittle would be, there are 10 reds, so 10 out of the total. So 10 plus 8 plus 6, we're up to 24, plus 11 plus 9, that's 20 more, so that would be 10 out of 44. And I just want to double check that. 10, 8, 6, 24, yep, 44. So the probability that you select a red Skittle is 10 out of 44. And then when you select a green one, there are 44 in the bag again because you put that red one back. So the probability of selecting a green would be 6 out of 44. So we end up with 60 out of 44 squared. Which is 1936. The year your math teacher was born. Okay, and then that reduces down. You can reduce that on your own. So the next question is, what's the probability you pick an orange Skittle, eat it, and then select a purple Skittle? So this would be a dependent event because the first draw affects the second one because you eat that Skittle. So now there are less Skittles left in the bag to choose from. So this would be considered a dependent event. Okay, so let's lower the screen here. The probability of selecting an orange Skittle, there are 9 orange Skittles out of 44. And then after that you select a purple Skittle. Well, there are 11 purple Skittles left out of, there are only 43 Skittles total in the bag. So it ended up being 99 out of 44 times 43. It's going to be 18. I'll cheat. 44 times 43. 1892. Alright, cool. So the top one, this would be an independent event. That's a classic independent event because the first pick has no bearing on the second pick. You put it back. The bottom example, this is a dependent event because the first draw affects the second draw because you've eaten that Skittle now. Alright, let's keep plugging along here. What's the probability you select a red Skittle, eat it, and then select a brown Skittle? So the probability of this is just 0. The reason why is there are no brown Skittles. So you don't really have to go through any math. I recognize there are no brown Skittles, so the probability of this one is just 0. Alright, so this leads us into dependent events. Two events where the outcome of the first event affects the outcome. I think affect is, yeah, is that spelled wrong? I think so. Affects the outcome of the second event. So an example would be selecting 2 items without replacement. So I've got a couple examples here, and let's determine if these are dependent or independent. If you're choosing 2 prom dates, one after the other, from 15 potential dates, so you've got 15 people to choose from, and you're going to select 2 of them. So if you selected, let's say, this is a problem I had in high school all the time. If I selected, let's say, Michaela for my first date, does that affect the second choice? So the answer would be yes, because I've already selected one person, so now I only have 14 people to select from. So this would be a dependent event. Alright, let's go over to this one. Randomly selecting a spring break location this year and then another one next year. And you could go to the same place. So I'm randomly selecting a spring break location. So I'm just going to randomly pick Cancun. And the next year, I'm going to randomly pick, and it doesn't matter. Because the next year, I could go back to Cancun or I could go to Lutsen or something like that. So this would be an independent event, because the first selection has no bearing on the second selection. Okay, selecting a captain, then assistant captain for your kickball team. So if you selected Mary for the captain of your kickball team, that affects the assistant captain position because you can no longer select Mary for assistant captain. So this one would be a dependent event as well. The first selection, whoever you selected for captain, does affect because you have one less person for assistant captain. And the next one, catching fish in the lake outside the nuclear power plant. So this one, I believe it's independent because you're going to put that fish back every time. If not, I don't know. I don't really want to eat fish out of a nuclear power plant lake. They might have 3 eyes or something like that. So this would be you catch a fish, you put it back, and then you could catch that fish again. So that would be independent because you're not you're not eating that fish or keeping that fish. So it's totally independent because the next draw, the next fish could be the same one you just caught. Alright, we're almost done. What's the probability that you get the first 2 problems right on a matching quiz that contains 8 questions? So matching, we'll kind of think of it as in terms of blanks. How many choices do you have for that first question? And you're just completely randomly selecting. You did not study. You have no clue what they're asking on the test. So I'm just going to randomly select. I've got 8 choices for my first answer. It could be A, B, C, D, E, F, G, or H. And then, oops. And then on my next one, I have 7 choices. So this would be considered a dependent event, because if I selected A, then I can't select A again. It would be kind of silly to do that because it's a matching one. You're not going to, match up the same definition with 2 different words. So this would be a dependent event. This also ends up being a permutation. So it would be 8 times 7, which is 56 ways to answer the first 2 questions on a matching quiz with 8 questions. Alright, so on to the last basically series of questions for the day. BHS has 504 athletes currently. There are 243 students involved in clubs, and there are 89 people who do both clubs and athletics. So make a Venn diagram for this situation. So I know 89 is going to be the middle number where the 2 circles overlap. And then there are 243 students in clubs and 504 in athletics. So my Venn diagram, I'll give you a second to fill yours in. So make a big circle, another circle, and fill in the numbers. So my Venn diagram looks like this. There are 89 in the middle, and then the 154 comes because in this blue circle for clubs, that has to add up to 243. So I wouldn't put a 243 here. I'd actually put a number here that makes 89 plus 154. That ends up being 243. So this whole blue circle adds up to 243. And the whole red circle adds up to 504. So basically we did 504 minus 89, that gave us 415. And 243 minus 89, that gave us 154. Okay, so this is the last idea of the day. Find the probability of A slash C. So the way this is read is the probability of A given that C. In other words, I want to know what's the probability that somebody is in athletics if I tell you that they have to be in clubs. And so what that means is we're only choosing from this blue circle. So on the next slide it kind of shows us that a little better. Probability of somebody is an athlete given that they are in a club. Well, there are 243 people in clubs and 89 of them are athletes. So the probability of somebody being an athlete given that they're in a club would be 89 out of 243. So the way I like to think about this is I told you I selected somebody at random and they are in a club. So then the next question is, what's the probability that they're an athlete? So if you know they're in a club, that's only the club circle, that's 243. And how many of them are athletes? Well, it's the 89, so the probability that they're an athlete given that they're in club would be the 89 over 243. Alright, so what about a probability of C and A? So what that means is that they're in clubs and athletics. So that would be 89 people are in both out of the total number of students. So the total number of students is 415 plus 89 plus 154. So let's add that up. 415 plus 89 plus 154. And that's the total number of students here at BHS in athletics and clubs, so 658. So the probability that you select a random person and they're in clubs and athletics would be there's 89 people that are in both out of a total number of 658 students. Okay, last one. What's the probability that somebody is in clubs if you know that they are in athletics? So I'm telling you they're an athlete. That means that there are 504 total athletes. What's the probability that they are in clubs? Well, there are 89 people that are in clubs. Alright, good luck. Hopefully you were able to catch up or kind of keep up. If you weren't, feel free, this video is posted on my website, feel free to watch this video again tonight sometime to help make it sink in. Alright, we'll see you tomorrow.